somebody say something really stupid.
No. All right, so really quickly, we're going to go through this review. If you guys have questions going over it, ask. But what I need you to do is make sure that you actually are actively looking for what mistakes are different, right? Like, what did you do yesterday that was different than what we're going over in the review? Because that's the stuff you need to clean up. So ask questions about that if you got it wrong. So real quick, we'll go through these. Question number 1 was, what does the slope of a displacement versus time graph represent? Displacement versus time graphs are talking about position versus time. So it's one of these graphs where we put like where the object was at different time intervals. The slope of a position versus time graph, right? You have to do rise over run. So you have to go up and then across, right? Rise over run. Well, that's the same as your change in x, how much you change your position, divided by how much you change your time. That ends up being the equation for velocity. It's x over t. So the answer to this, what does the slope equal? It's the velocity. On a displacement versus time graph, where we're looking at position of objects, you're actually finding the velocity if you find the slope on that graph, because you're doing distance, position, divided by time. Number 2, what does the slope of a velocity versus time graph represent? Well, you take the same method, you look at it the same way. So on a velocity versus time graph, you've got v over here, you have time here. And if we want to know what the slope is of one of these graphs, same thing, right? You're looking at rise over run, so you're going to rise up and then go across. Well, look, the rise has to do with velocity. Rise over run. So instead of saying rise, I'm going to put velocity over time. The run is time, right? So rise over run would be velocity over time. That equals your acceleration. So the slope of a velocity versus time graph is acceleration. Okay? What are the 3 ways an object can accelerate? Well, if you've ever driven in a car, you know the 2 ways that are very obvious deal with your feet, right? Your controls at your feet. What are things you can do to change your velocity with your feet in the car?
Increase the pressure on the gas.
So gas, right? So that's increasing your velocity. So you can increase your velocity to change your acceleration. So if you can increase your velocity, there's another pedal down there that does what to your car?
Decreases.
It decreases the velocity. So you can increase your velocity to cause an acceleration, or you can decrease your velocity. Now the third way that I didn't see anybody put on their paper, but you guys remember velocity deals with your speed, the magnitude of how fast you're going, and the direction. So if we change our direction, even though we keep the same speed, that counts as an acceleration. Okay? That counts as an acceleration because it's a vector quantity. So if you change your direction, that is also an example of acceleration. Even if you were in cruise control, started turning, during that turn, you would experience an acceleration. Your body would change its velocity. And I'm not going to stay too long on each of these because I am recording it. So you'll be able to go back and watch it over and over if you want. See how many views you can get on there. All right, so right here, number 4, it says that using the graph above, describe and calculate the object's acceleration and displacement. Well, we just said the acceleration on a velocity versus time graph is the slope. So we need to find the slope of this graph. So we start at the beginning and we look at the last point, these 2 points on that line. We would do rise over run to find the slope. It goes up 20, then it goes across, it runs across 5. So our acceleration here is just going to be the rise over run, 20 divided by 5. So it's going to be 4 meters per second squared. That would be our acceleration. The displacement remember we said for displacement in our notes when we had taken these, and they're also on our website, you can go back and check. The displacement is equal to this area underneath here. All this stuff here is x. It's how much displacement you have from where you started. So to find the area under that curve, you have to look at what shape it is. Is it a rectangle, a triangle, what shape is it? And then you use that equation for area to tell you what to use here. So this is a triangle. The equation for the area of a triangle is 1/2 base times height. So for our problem here, it would be 1/2 times 5, the base, times the height, which is 20. 20 times 5 is 100, times 1/2 is 50. So it ends up being that our displacement is 50 meters for that part. Okay? For sure there'll be some stuff like this on the exam as well, so you want to be familiar with how to do that. Okay. For number 5, it says you've got an acceleration versus time graph, and we need to find the velocity, the acceleration, and describe what's happening along each point. So acceleration is how quickly you're accelerating, how quickly you're changing your velocity, right? It'd be like if you barely push on your gas pedal, would be like a small acceleration. And if you were jamming on the gas pedal really hard, that would be like a high acceleration, right? You change your speed faster. If you have a big acceleration, you change your speed lower with a smaller one. Okay, so the important thing to understand here then is if we're trying to find out what our acceleration is, this object, it's going, what's happening to acceleration? The acceleration is increasing, so that's the first thing, right? We can describe that. If we had to describe the velocity of this graph, we would show that the velocity was increasing slowly at first, but then it starts increasing faster. It would cause this little curve right here. See, right here, the velocity is getting faster and faster and faster at a faster rate because you have a bigger acceleration, whereas down here, it's slower, more gradual because you have a lower acceleration at 1. Okay? So this would describe how the velocity is going to look. Draw a little graph to show that. And then the last thing, can we tell what direction this object is going? Because it has a positive? On this graph, I'm glad you said that because I want that to come up because some people will think that if we have a positive number for acceleration, that means that you are getting faster. Doesn't tell you anything about direction, okay? If you had a negative number for acceleration, let's say that the graph went down here somewhere, well then here, where it was negative, that would mean that the object was getting slower. It will not tell you direction, okay? So an acceleration versus time graph isn't going to give you a lot of information about what direction the object was going, okay? It might have been speeding up or going backwards, you're not sure. You can only tell if it was going faster or slower, if it was getting quicker or slower. So that's something to be careful about with these, right? Because on the velocity versus time graph, if it was positive, that meant forward. If it was negative, that meant backward. It changes when you're dealing with a different thing on this axis. All right, y'all are doing good. So on number 6, let's take a look at this one. It says to describe the velocity for those intervals. It's a displacement versus time graph. So to find the velocity, we have to look at which part of the graph. The what? Okay, yeah, so we're going to be looking from here to here, right? 0 to 5 seconds. So this point on the graph to here, how can we find out the velocity from that point? Rise over run, we find the slope. So it's going to go up 5, and then it's going to go over 5. So the velocity from this time interval will be 5 over 5, which is 1 meter per second. Just like that. And then from 5 to 10, from this point to this point, is there a rise? No, right? So it's going to be 0 divided by 5, which is going to be 0. So the velocity right here is 0. It's not moving. And then from 10 to 12, from here to 12 and a half, it goes down 5, so that's negative 5. Then it goes over 2.5. So you do negative 5 divided by 2.5. That gives you negative 2 meters per second. The negative here is going to tell us that that object was going backwards during that point. Okay? So right here, the downward slope is going backwards. And we did this in front of the motion detector. Remember, we're walking back and forth. And when you walked back towards the motion detector, it brought your graph down, right? Negative slope. And when you're walking away from the motion detector, it looked like that, positive slope. All right, number 8, this is a velocity versus time graph, but you do the same type of things, right? You find slope, you look underneath the curve. And in this case, on the velocity versus time graph, acceleration is the slope. So from 0 to 2 seconds, the object goes up 2, over 2. So the acceleration will be 2 over 2, which is 1. The displacement, what do you do for displacement? That's x. So you're looking at the area under the curve. So from 0 to 2, this is our line. So we're going to look at all the stuff underneath it right there. It's a triangle, a little triangle. So you're going to do the 1/2 base times height because it's a triangle. So 1/2 times 2 times the height of 2 is going to give you 2 times 2 times 1/2 is 2. So this is going to be 2 meters for your displacement. So to find displacement, you're looking for area. To find acceleration, you're looking at the slope on the graph, okay? From 2 to 3 seconds, from right here to right here, well, this part right here is a rectangle. It's not a triangle, right? And there's 0 slope, it's flat. So we're gonna end up with 0 over 1 for the acceleration, that's 0. It wasn't getting faster or slower. It was just staying the same speed.
Oh, what question are we in?
This is question, what was it? We'll go back and look at it right after. All right, and then the displacement, the area of this piece right here, these two boxes, it goes up 2 and over 1. So it's going to end up being length times width because it's just a rectangle. You don't have to do 1/2 base times height for a rectangle to find an area. We did that with our investigation outside, right? That was the purpose of using that as our starting point. So if we do length times width, it's just going to be 2 times 1, which is 2 meters. From 6 to 10 seconds, we have a slope right here. It's going to be -4 divided by 4. -4 over 4 is equal to -1 for the acceleration. If you have a -1 for acceleration, that means you're slowing down. You're getting slower, you're hitting the brakes. Okay? The area under this curve will tell us the displacement. So we're going to use the 1/2 base times height because this is a triangle, right? Underneath that curve, it's a triangle. So we're going to do 1/2 times the base of 4 times the height, which is 4 units high. So what's the area of that? What is that? 8. Good. Okay, so that's how you can evaluate different information from the velocity versus time graph. You do the same thing. If it goes negative, it goes down here. This part down here where it's negative just means that you're going backwards, right? This whole time, the object was moving forward. Even though it's going down here, don't forget, these are velocities, they're not positions. so it was just getting slower. It wasn't going backwards yet. It doesn't go backwards on this graph unless it goes into negative numbers for velocity. Okay? So that was number 8 now. All right, and just to, so those are all the graphing questions that you might have to see on the test. Nothing other than that will show up. So as long as you focus on that stuff at home, you should be all right. For 9 through 13, if you just look at your equations as we go through it, you can keep me honest, make sure you put the right equation. I'm going to go through them pretty quick though. If you have a question as we're going, like why did you pick that number? Is this variable? Let me know, and I'll explain why. So right here, this 450 meters is a position. It's a displacement value of how far the object moved. They experienced an acceleration, and they give you that acceleration, 0.77. They tell you the initial velocity was 34.9, and they want the final velocity, VF. So once you know what variables you've got to look for, you find the equation that has those variables and you use that. So in this problem, we need to find VF. So there's an equation that solves for VF, and you just need to know the initial velocity and square it, and you add 2 times the acceleration times the change in position. That's the best equation for this problem because it has position, it has displacement, it has acceleration, it has initial velocity, and it even already solves for the final velocity. You just gotta plug things in to get the answer. And you should try it on your calculator as I do it. Let's see if we get the right thing, the same thing. So when we plug in our values here, and on the test it'll be multiple choice. You won't have to show all your work, but make sure you still do it to check your work after you're done. So this would end up being 34.9 squared plus 2 times 0.77 times x, 450. Do one more thing. So you should get 43.7 for your final velocity, meters per second. Number 10 says that you have an object traveling at 56.02 meters per second. That's your initial velocity. It experiences an acceleration, that's your A, for 2.7 seconds is your time. And you need to find the distance, x, is what you're looking for, that the car traveled in that time. So for this problem, we're going to be using the equation that solves for displacement, that uses initial velocity and time plus 1/2 AT squared. This equation is the best one because it has time, it has acceleration, it has initial velocity, and then it also gives you what you're looking for. So you just have to plug them in. There's always going to be a situation when you put stuff, when you look for the equation, that none of them will make sense except that certain one. So when we plug in our numbers here, it's going to be 56.02 times the time of 2.7 plus 1/2 times the acceleration times the time squared. And that'll give you your displacement. Should get 120.3 meters. All right, and then number 11, a man is running at a speed of 3.05 meters per second. He gets faster, he speeds up to a new final speed of 5.3 meters per second. He does that in 2.5 seconds. They want the acceleration, so that's what you're looking for. The equation that solves for acceleration and uses time is the one that says VF minus VI over T. So we plug in our VF minus VI, that would be 5.3 minus 3.05. divided by the time of 2.5 seconds. And that'll give us our acceleration for this. It's getting faster. You should get 0.9 meters per second squared for the acceleration. So just a couple more. Number 12 says that an object's dropped from 600 meters. So that's our position change, x. They say that it starts at rest. That's your initial velocity of 0. The top speed, the final speed is 45. And we want to know, just as it hits the ground, what is its acceleration? So to solve for the acceleration here, there's an equation on your sheet that uses final initial velocity that we could use for this equation, right? And that would be x equals vf squared minus vi squared over 2a. So when we plug everything in, it'll be 600 equals 45 squared minus 0 squared divided by 2 times a. Remember, we said the first step we should always take is simplify everything. So if you can multiply, subtract, do stuff with numbers and make it look easier, well, that's what we do. And in this case, when we simplify it, it'll be 600 equals 2025. When you simplify the top, you get 2025. Put in your calculator. Divided by 2 times a. Now we need to get a on top, right? So what you do is you cross multiply, and you end up with 600 times 2a. 600 times 2a is 1200a, right? Just 600 times 2 is 1200. And then this number, 2025 times 1, is 2025. So to get the a by itself, what do we do? You divide both sides by what? By 1200. So over here, you're going to end up with a is equal to 2025 divided by 1200. You get 1.7 meters per second squared. All right, and then the very last problem deals with relative velocity. It's what we covered yesterday in class. Relative velocity has to do with your speed in relationship to other things. We talked about that and how that's different. So in the example problem that y'all did yesterday, or the quiz problem you did yesterday, it says that you have a train moving towards a train station. It's moving 50 meters per second. Right, so you got the train, and the train is moving at 15 meters per second, and then you're on the train and you're moving 5 meters per second, right? There's a person on the train moving 5. This happens for a total time of 2 seconds. And they want to know how far did you go, like what was your distance traveled relative to the station, okay? So there's this big station over here. So relative to the station,
40 meters?
how fast, how much distance did the person go?
40.
They didn't ask for the car, they asked the person. So,
so 10.
so you think, okay, that's good. But if this is going 15 and this is going 5, how fast would it look like to someone in the station? It would look like they were going 20. If they were just only looking at this person and measuring them somehow with a radar gun, only the person, not the train, they would see that the person was moving 20 compared to them, okay? The train's moving 15, yes, but they're moving 5 forward on top of that. So it'd be like if they had a velocity of 20 meters per second. They have a time of 2 seconds. The equation for x, right, that has that is this one, v equals x over t. So we just plug these numbers in here. It'll be 20 equals x over 2. So what is x? You multiply both sides by 2. So the displacement ends up being 40 meters. And they can try to change this question to make it more complicated. They could say, how much distance did the person travel relative to, another person on the train? Well, then you don't use 20 as the velocity, you use 5. Because compared to everyone on the train who's just sitting down, this person's only moving 5 faster. So compared to them, he'd only move 10 meters away. Okay? So the way they word this, relative to what? Whatever it says it's relative to is going to change your answer quite a bit. Okay? Just like I said right now, remember when we talked about this the first time, your velocity is 0 right now. So compared to me, you're not moving at all. But if I was standing on the moon, well then your displacement compared to me would be huge because you're moving very fast compared to someone standing on the moon. Okay? Does anybody have any questions?